January 14th, 2017, I printed this paper out, Coreless Terrestrial Exoplanets. Accepted it, Astrophysical Journal. Doesn't really matter who it's written by, the information is what I'm going to be attacking. The abstract. Differentiation in terrestrial exoplanets is expected to include the formation of metallic iron core. We predict the existence of terrestrial exoplanets that have differentiated but have no metallic core. Planets are effectively a giant silicate mantle. A few problems with this. Firstly, they don't approach it from a galactic worldview. How should I say? When they're looking at these objects, they're looking at it, well, a bunch of preformed rocks clump together and make a larger, bigger rock. There's no depth to their analysis here. And for this talk, I want people to realize that if they're going to pull this paper up, look for what they're not saying. They're not going to talk about gas deposition. They're not going to talk about plasma recombination. They're not going to talk about ionization potentials of the material and why that should differentiate versus just talking about solid and liquid material only. They're only going to look at it from a myopic standpoint because that's all they're allowed to talk about. When you get papers published into Astrophysical Journal, you have to only publish what they allow you to publish. And stepping outside of those bounds is very bad news. In the introduction it says here, understanding the interior composition of exoplanets based on their mass and radius measurements is a growing field of study. While over 30 transiting exoplanets have measured masses and radii, all are between Jupiter, which is 11.2 Earth radiuses, and Neptune. No, 11.2, that's about right, and Neptune size. And that's problematic too. I mean, this paper was written in 2008, so it denies hot Jupiters, which are Jupiter-sized objects which are probably more massive than Jupiter. They're orbiting very, very closely to their host star, which means their outer gaseous atmospheres are being ripped away. So hot Jupiters aren't mentioned here. And then it says here, for a solid planet with a given mass and radius, planet interior models aim to provide the mass fraction of planet building materials typically assumed to be iron, silicate, and water. Now, they think planet building materials are what the planet is currently comprised of. So if they see an Earth-sized object, which is mainly silicates, which is mainly water, which is mainly iron, nickel, magnesium, that kind of stuff, they're only going to say, well, that's what the material or what the planet is made out of. And that's how it's always been. It's that uniformitarianism that geologists accept. They don't realize that to make something that's very rocky like that in outer space, it looked a lot different. Very early in the star's history, it was mainly comprised of hydrogen and helium, and various other low-density gases, volatile gases, that have been already ripped away long, long before the interior started showing itself, the rocky metal interior started showing itself. So they don't look at that at all. They don't look up at the sky at night and say, well, look at those bright things that are mostly hydrogen and helium. What if asteroids that are iron enter into them? Where would that iron go? Well, clearly it would go towards the center, and that's where the accretion happens. It's inside the star itself, inside the gas giant, and over time that outer thick hydrogen helium atmosphere gets ripped away, exposing the rocky silicate, iron, and watery interior. But that's completely lost upon them in this paper. Another issue here, this is on page 2 if you want to look at it yourself. Differentiation in terrestrial planets is expected to include the formation of a metallic core. Obviously, if it had enough time to form one, it will have a very big metallic core. The terrestrial planets differentiated early in solar system evolution to have metallic iron cores and silicate mantles. Again, a very large problem. I don't know if you guys saw that. It says here, early in solar system evolution. They look at the solar system as being a single object. That's a very false worldview. The solar system is comprised of multiple objects, all in different stages of their own evolution. The Earth is very, very old, the Sun is very, very young, and the other objects are older than the Earth or younger than the Earth. And all of them are basically older than the Sun. But that's completely lost upon them. Also, they have here, planetary differentiation is driven by density alone. Metallic iron is denser than any mantle silicate material at any pressure. Well, obviously, but given the star was comprised of hydrogen, helium, and other very lighter elements in its past, and those elements were very, very energetic, meaning if there was iron in there, it would be plasmatic. It would be subject to electromagnetic forcing as well, meaning the process of differentiation is not only density dependent, it is also a property of what the material is when it's ionized, how well electromagnetic forcing impacts it, how well it interacts with other metals or other material to form larger molecules, and which molecules form first as it differentiates. Also, the purity of it, okay? It says here, its migration to the planetary core, speaking of iron, would require melting of the metal and likely of the silicate portion of the planet as well. So obviously it's going to, need to melt. The iron's going to need to melt. But how do you get the iron to melt? Obviously they have no method for melting it. There's no giant furnace in outer space that can melt all that iron down. So how do they melt it? They don't ever say. Clearly, it's a young hot star that can melt down all that iron when it falls towards the center. But melting is only one phase transition as well. You take something that's solid and you melt it into a liquid material. That being said, you can automatically tell right off the bat that they're being myopic with that as well. It's because if the star was made of plasma, it means you had to undergo plasma recombination, meaning the plasma becomes gas as it neutralizes, and then that gas deposits as pure material. That's called physical vapor deposition. Instead of young hot stars, the physical vapor deposition of an iron core begins around red dwarf stages of star evolution when the iron nickel core begins forming. That's why that material is really pure. If it didn't, there wouldn't be a pure iron nickel core, and there wouldn't be a core to begin with, such as this paper, predicts, a coreless planet. Not being hollow, but coreless meaning no iron nickel in the center, but mostly silicates. You need to have physical vapor deposition to make something as pure as an iron nickel core. These other pages go over a few specific gravities of the material, how heavy some of the material is, noticing some other people's work, the viscosity of materials given certain temperatures, different models, things like that. Oh, here's a good bit. It says here on page 6, towards the middle of the page, is 3.1, detailed interior density structure model. This is the third paragraph down. Planets are assumed to form from planetesimals, created from materials similar to the chondritic materials, meteorites, from the collection of falls found on Earth. These meteorites represent primitive, undifferentiated material from the time of planetary accretion. Again, they form Earth-sized objects from preformed rocks, preformed solid, pure iron nickel stones that are floating in outer space. How the hell did you form those stones? In my backyard, I remember making a little copper aluminum foundry, air blast furnace kind of thing, where I took a can and I lined it with refractory material. I put a hole in for the air blower. I put in some coal and I put a steel container in there, which I melted the aluminum and copper inside, and I closed it. So there was a lot of heat. There was a lot of air going in there, oxygen burning. There was a lot of pressure in there, from our atmospheric pressure, mind you, at least one atm. But in outer space, you don't have any of that. You have vacuum. You don't have any air in there. You don't have any pressure. You don't have any fuel to melt down the iron. So how the hell did purified pieces of iron nickel form in the dead of outer space? They have no explanation for that. They have no understanding of what it means to make an Earth-sized object from those little purified iron nickel balls. So they literally say the accretion happens with those first, which they have no method for forming, and then they magically clump together. These people have lost it, man. They don't know anything about how to work metal. Yet they're at MIT, for God's sakes. Maybe they should go to an iron worker factory or some type of place where they melt down large bits of metal so they can see what it takes to melt down that amount of iron. But here's a summary, page 11. We hypothesize there are 2 accretionary paths to a coreless planet. Obviously, their accretionary paths don't include the majority of stellar evolution, which means that they're not actually paths at all. They're just ignoring observations. And obviously, they assume that the solar system is a single object, and they assume a whole bunch of other things that they had no information on. Basically, this paper is just a bunch of assumptions and grasping for information that they don't have any information for. Alright, I'll go ahead and link this paper to the bottom of the page or of this video. Take it easy, y'all.